All right, I'm going to describe the steps of a lab that we've been developing that is geared towards students in a first year, second term astronomy class, where students will use telescopes on the Skynet Robotic Telescope Network and tools developed by Skynet for analysis, for photometric analysis, to eventually produce color images and color magnitude diagrams and do some isochrone modeling to determine cluster parameters. So this is a project that I piloted this past term with my students at the University of Saskatchewan, and just show basically how it works. So students first of all, go to Skynet and submit observations using Skynet telescopes. So I set up an observation a couple of days ago of the star cluster NGC 3766. So basically how it works is you do a search and Skynet's object database pulls up the right ascension declination coordinates. It can change various settings. Lunar avoidance, set up dithering if you want to do that, or it's possible later on to set up an image sequence, which allows for different sky conditions and potentially better ideal conditions at times for images to be taken. And so once you've done the search, there's a target visibility chart that shows that this target's up for a number of hours throughout the night with these conditions. You can choose telescopes, filters, and then later on settings for exposure durations, how many exposures to collect, whether the observation is repeated a certain number of times, etc. So here's the observation. These are sort of my list of recent observations, and this is the one that I set up, like I said, a few days ago. Here are some of the recent images that were taken. I set up a sequence with repeat every hour or so in BVRI, and so these were taken, a few days within the last few days. Here's my observations file, and then once the observations come in, then we move over to Skynet's Afterglow website, which is the FITS image analysis site. It's web-based and it is openly accessible using a Skynet account, which can be set up for anyone. And so you can see here I've got my observation there. I set up 10 repeated observations in B, V, R, and I, and so there are 10 images in each of them. Well, there's kind of an ugly one all here, and so as I flip around, you can see that it sort of moves around. Some of the images are worse than others. There is a bad pixel. Anyway, so we can take all of these, reduce some noise by doing some stacking and aligning and stacking. And so in this site, we can use these different tools to get an updated WCS registration through astrometry.net, align images, and stack images in different filters. So here's settings for just a basic median if I wanted to do that, among other things. And then some of the tools that that have only just been recently developed are still here on the development site, where I've got my aligned and stacked BVRI images loaded. And on this site, click there, gotta wait for it to load because there's a whole bunch of information going on. Here are my basic aperture photometry settings. So I've set up adaptive aperture, so it'll adjust the aperture size to do and ellipticity to do aperture photometry, and automatically calibrate using a catalog selected from a list. For BVRI, I used APAS, and a number of other settings that can be set, source extraction settings to deblend and discard saturated sources, and then automatically extracted all of the point sources from this field. There are 3574 stars that were extracted in this field, I think based on the eye image, and then I automatically photometered them. And so I just did this morning, but I can download the batch photometry data file, which has calibrated magnitudes for all of these 3,500 stars in this field. And then once I've got that, I can go over to the Skynet plotting site that's been set up here, where I can upload my data file, and so there's the one that I just finished. And here you can sort of start to see this this cluster's HR diagram. And the main sequence there, and then we've got a number of tools for as the loading takes a couple of minutes because this site auto matches to a Gaia database, and so we have proper motion information over here and distance here, and you can see that the site actually does a pretty good job of zeroing in on the cluster. So those are proper motions of stars all over. And as I zoom in, reset. When I zoom in, you can see the cluster sort of, the main clump is already zeroed in on by the site. And if I zoom in on it, drag over, I think I need to go to about there, and that centers on that clump of stars, and then I can get rid of stars that are not within that proper motion window, and so I just want to see the stars that are in that clump, and by eliminating the stars that are outside of that clump, you can see the main sequence emerge already right away. And that enables us to go over here and find the distance. Again, this is comparing to Gaia distances. And so if I set my tolerance to about 20%, that enables me to find the cluster's distance by locating where the cluster shows up. So it kind of goes away around 1.8 or so on the low end, and around 2.5 or so on the high end. And so the cluster's distance seems to be somewhere around 2.1. I might set it at. And once I've done that, I can adjust the age. This is an isochrone model here. And so I can use it to get an idea of the cluster's age. I should have changed. We've got two different color magnitude diagrams, and I photometered in 4 different filters. And so if I set up a graph of R minus I versus I and B minus V versus V, we can determine the cluster's parameters fairly easily. So once we've got the distance, this looks roughly like the age. Metallicity is going to affect things, and that's probably much higher than that. And here we start to see something that looks like that cluster. By maybe something like, sorry, if my reddening is something like that, And then maybe the cluster's a little bit younger. I want to catch those two red giants if possible. You know, maybe something like that with a little bit more reddening. Anyway, the isochrone model goes below the main sequence because of binary stars that lead to the scatter here, and I can flip through my various V minus I versus I, B minus I versus I, B minus R versus R, and V, different colors. So I might have to adjust a couple of settings, but can get a pretty good fit to this cluster to determine its parameters, which are going to be somewhere around there. And in addition to this, another tool that I skipped over here is I can also create a nice color image using Afterglow. So if I go to the display tab here, I think, and pull this up, this blue, green, and red are just my stacked B, V, and R images, and I've combined them together to create a color image. And so students are able to look at this color image, see that there are these couple of red giants, and the brightest stars are these red giants and a blue giant in this cluster, and compare and see that's exactly what shows up here in the color magnitude diagram.